A graph of an equation is a set of points representing its solution set. Each point on the graph corresponds to an ordered pair that is a solution of the equation. By graphing two equations using one set of axes, we can identify a solution of both equations by looking for a point of intersection. So here we have two linear equations. Using one of three graphing methods, we can graph this line either by points, by intercepts, or putting it in slope-intercept form and using slope and y-intercept. This first equation graphs as follows. The second equation graphs as shown here in red, and if you notice, these two lines do intersect, and if we read the ordered pair or the coordinates of this common point for these two equations, we find that the point 2, 5 is a solution for both of the equations. To check this, a solution to a system of equations has to be true for both equations. So replacing 2, 5 for x and y respectively in the first equation, we get a true result. Replacing x with 2 and y with 5 in the second equation and simplifying, following the order of operations, we find that it is also true. So here we have the one solution to these two equations when solved simultaneously, shown here using the graphical method. Let's look at another example. To solve this system of equations, we're going to graph each equation. The first equation here graphs into the following, and recognizing that this line is an infinite set of points that satisfy this equation. Likewise, taking the second equation and graphing that linear equation results in the following line. Here we have a situation of parallel lines where there is no common point between those two equations, and that tells us that there is no solution to this system of equations. There is no common point that will satisfy both of the equations. The other thing to note here, parallel lines have same slopes. What we have to look out for is that they have different y-intercepts, which is the case here. Moving on then, let's look at a third example where we have two lines. Again, to find a solution to this system, we'll graph each line. Here in green is the graph of all the infinite number of solutions to equation number 1. And when we graph the second equation, if you noticed, it happened pretty quickly, this red line is superimposed, or in reality is the same line as the graph of the first equation. What happened here is that we have lines that coincide. Essentially, they are equations of the same line in different forms, and in terms of a solution, we have an infinite number of solutions that will satisfy both equations since they are the same line. Any point on one line would be a true solution to the other line or equation of that line. For example, here we have the point 0, 2, and just to verify that, replace x with 0 and y with 2 in the first equation. Simplifying gives us a true expression, and likewise if we replace x with 0 in the second equation and y with 2 and simplify, we have a true expression as well. So verifying that this point is a solution to both of the equations, and as a matter of fact, any point on this line will be true for both of these equations. So we have an infinite solution to this system.